Next chapter, Similarities and Enlargement. Similarity of figures. Two triangles are said to be similar if their corresponding angles are equal and their corresponding sides are proportional. In triangles A and PQR, if angle A is equal to angle P, angle B is equal to angle Q, and angle C is equal to angle R, and that AB over PQ is equal to BC over QR is equal to AC over PR, then triangle ABC is similar to triangle PQR. Conversely, if triangle ABC is similar to triangle PQR, then angle A is equal to angle P, angle B is equal to angle Q, and angle C is equal to angle R, and AB over PQ is equal to BC over QR, and it's equal to AC over PR. Notice that by corresponding sides, we mean the sides opposite to the equal angles. Let us learn something about three similarity postulates for triangles. The SAS postulate. If two triangles have a pair of corresponding angles equal and the sides including them are proportional, then the triangles are similar. In triangles ABC and DEF, if angle A is equal to angle D and AB over DE is equal to AC over DF, then triangle ABC is similar to triangle DEF. Equally, if angle B is equal to angle E and AB over DE is equal to BC over EF, then triangle ABC and DEF are similar. Lastly, if angle C is equal to angle F and that AC over DF is equal to BC over EF, then triangles ABC and DEF are similar. SAS simply stands for side angle side, that is two sides and the included angle. The AA postulate. If two triangles have two pairs of corresponding angles equal, then the triangles are similar. In triangles ABC and DEF, if angle A is equal to angle D and angle B is equal to angle E, then triangle ABC and triangle DEF are similar. This also means that even the third pair of angles are equal. So the postulate can also be called AAA postulate. The SSS postulate. If two triangles have three pairs of corresponding sides proportional, then the triangles are similar. In triangles ABC and DEF, if AB over DE is equal to BC over EF, which is equal to AC over DF, then triangle ABC is similar to triangle DEF. Theorem on right-angled triangle. A perpendicular drawn from the vertex of the right angle of a right-angled triangle divides the triangle into two triangles similar to each other and also to the original triangle. In the right-angled triangle ABC, AD is perpendicular to the hypotenuse BC. Then, triangle ABC is similar to triangle DBA. Triangle ABC is similar to triangle DAC. And triangle BDA is similar to triangle DAC. By the definition of similarity from equation 1, we shall get AB over BC is equal to BD over AB, cross multiplication, AB times AB is equal to BC times BD. So we get AB squared is equal to BC times BD. From equation 2, we shall get AC over BC is equal to CD over AC. Cross multiplication, AC times AC is equal to BC times CD. And so we get AC squared is equal to BC times CD. And from equation 3, we shall get AD over BD is equal to CD over AD. That shall give us AD squared is equal to BD times CD. The basic proportionality theorem. A straight line drawn parallel to one side of a triangle divides the other two sides proportionately. In triangle ABC, if DE is parallel to BC, then AD over BD is equal to AE over EC. It follows that AD over AB is equal to AE over AC and it's equal to DE over BC, since triangle ADE is similar to triangle ABC. The converse of the basic proportionality theorem. If a line divides two sides of a triangle proportionately, then the line is parallel to the third side. In triangle ABC, if AD over DB is equal to AE over EC, then DE is parallel to BC. Now, enlargement. An enlargement is a transformation which increases or decreases the size of an object. Under an enlargement, the object and its image are similar. Corresponding sides on the object and image are parallel, and angles remain the same. An enlargement is defined by two components. One, the scale factor of enlargement, and this is the number of times the image is bigger or smaller than the object. A scale factor of 2 means the image is twice as big as the object. A scale factor of a half means the image is half as big as the object. And 2, the center of enlargement, and this is the point of reference and where all the distances are measured from. For instance, triangle ABC is enlarged twice, first to triangle PQR and then to triangle XYZ, with the center of enlargement at O. PQ over AB is equal to QR over BC and it's equal to PR over AC and it's equal to 2. So the first enlargement is of scale factor 2 about center of enlargement O. And so triangle PQR is twice as big as triangle ABC. Then XY over AB is equal to YZ over BC and it's equal to XZ over AC and it's equal to 3. So the second enlargement is of scale factor 3 about the center of enlargement O. Another important thing is that the corresponding image and object distances from the center of enlargement are proportional. So for the first enlargement, OP over OA is equal to OQ over OB and it's equal to OR over OC and it's equal to 2. For the second enlargement, OX over OA is equal to OY over OB and is equal to OZ over OC and is equal to 3. This is very important because it is this understanding that we use when enlarging shapes. Enlargement of plane figures. The nature of enlargement is critically defined by the scale factor and the center of enlargement. We have a positive and negative scale factor. Enlargement by a positive scale factor. In positive scale factor, the object and the image are on the same side of the center of enlargement. So in order to enlarge a shape, there are two things you always need to know: what is the scale factor and where the center of enlargement is. The scale factor of an enlargement is how many times bigger a shape has been made. What is the scale factor of enlargement of the pink shape? The pink shape has 1, 2, 3, 4 boxes down, and the blue shape has 1, 2, 3, 4, 5, 6, 7, 8 boxes. Now I know that 8 divided by 4 is equal to 2, and so the scale factor is 2. Remember, the ratio of corresponding sides must be proportional, so I could actually have counted the top line. So 1, 2 boxes, and 1, 2, 3, 4, or 1, 2, 3, 4, and this should become 8. 1, 2, 3, 4, 5, 6, 7, 8 boxes. So it doesn't really matter which side you count. It should always get the same scale factor if it's indeed an enlargement. What is the scale factor of these enlargements? We start with A to B. A has 1 across here, and B has 2 here. That should be enough to know. So that should mean A is half as big as B, or B is twice as big as A. Another way is 1, 2, 3. 1, 2, 3, 4, 5, 6 boxes. So the scale factor of A to B is 2. Now A to C. C has 1, 2, 3, 4, 5, 6 boxes, and A has only 2. So 6 divided by 2 is 3. You could also have counted these boxes and these boxes here. B to A. B is 1, 2, 3, 4, and A is only 1, 2. And so 2 divided by 4 is a half, or 0.5. How about B to C? If you count the bottom, C has 6 boxes, B has 4. So the scale factor is 6 over 4, which is equal to 3 over 2, or 1 and 1 over 2. So C is 1.5 times as big as B. Now, when the shapes are not drawn on a grid, it becomes more difficult to enlarge them. In such cases, we use projection lines, and at this point we will need the center of enlargement. This pink shape is being enlarged to give the blue shape. The center of enlargement is X. The scale factor is 2. So let us now enlarge triangle PQR with a scale factor of 2 about the center of enlargement X. First, draw a projection line from X to one of the vertices and extend it. We measure the distance XP is 2 centimeters. Scale factor is 2, so we double that distance and we get 4 centimeters. Notice that all distances are measured from the center of enlargement, and that is point P prime. Repeat the same for Q. It's 3.5 centimeters. Double that is 7 centimeters. That's Q prime. If you do the same for R, you will have R prime here. Now join the points to complete the image. Notice that because the scale factor is positive, the object and its image lie on the same side of the center of enlargement. We go to another example, but this time the center of enlargement is inside the figure itself. We will enlarge it by a scale factor of 3. The procedure is the same. Join X to M and extend the projection. Measure XM, it's 1.7 centimeters. Triple that, it will be 5.1 centimeters. And that's M prime. Repeat for N, draw the projection. XN is 1 centimeter. 3 times that is 3 centimeters. And we have N prime. If you do the same for O, O prime is here. Now join the crosses to complete the image. This time we do a scale factor of a half, so we expect the image to be smaller than the object. Draw a projection from X to A. Measure AX, that is 6 centimeters. Half that distance is 3 centimeters. And so A prime is here. We do the same for B. 5 centimeters. Half that is 2.5 centimeters. And that's B prime. The same for C, and C prime is here. Now join the points and complete the image. So the image is a half as big as the object because it's a scale factor of a half, but it is also on the same side of the center of enlargement as the object because the scale factor is a positive. Let us now do a negative scale factor. We do an enlargement of scale factor -2 about X. For negative scale factor, the image will come on the other side of the center of enlargement and will be twice as big as the object. So we draw the projections just as usual. We measure SX, it's 2.2 centimeters. Now double that distance. But you must measure all the distances from the center of enlargement. It's 4.4 centimeters. That's S prime. Repeat for T. TX is 3.2 centimeters. Double that from X, it will be 6.4 centimeters. And that's T prime. Finally for U, U prime is there. Now complete the image by joining the points. You will notice that in negative enlargement, the image is also inverted. So let's get clear how enlargement works. I have this object ABCD that has been enlarged to the image A prime, B prime, C prime, D prime. Down here I have a slide indicating scale factor, and it's telling us that the enlargement is of scale factor 2. Notice that it's positive and the image and the object are on the same side of the center of enlargement, that is the red spot. I'm going to move the slide to various scale factors and see what happens to the image. First, let's have the projection we had before. We go down to 1 3/4. the shape is reducing in size. 1.5, 1.25, and a scale factor of 1. So it's the same size and the same position. 3/4, a half, a quarter, and 0. There's no figure at all. And now we move to the negative side. -1/4, -1/2, -3/4, -1. Let's stop here for a while. At this scale factor, firstly, we have congruent shapes, meaning they have the same size and shape. And notice that the image is inverted. And you can see how that happened if you follow the points along the projection line. So A and A prime moving along the line and continues along that path. At the center of enlargement, the shape inverts. Keep going up to scale factor of -2. Yes, we have an inversion, but now the image is bigger than the object, twice as big. And so one common mistake is that students often think that negative enlargement means the image is reduced in size. No, it simply means it lies on the opposite side of the center of enlargement. And so that's what happens in enlargement. Next, areas and volumes of similar shapes. Let's go back to our triangle. If triangle ABC is similar to triangle PQR, then not only are the corresponding sides proportional, but the areas too are proportional. We've said that AB over PQ is equal to BC over QR, is equal to AC over PR, and is equal to the scale factor. This scale factor is known as the linear scale factor. If we square the linear scale factor, we get the area scale factor. The area scale factor is the ratio of the area of the two triangles. Mathematically, AB over PQ is equal to the linear scale factor. Then AB over PQ squared is equal to the area of triangle ABC over the area of triangle PQR. Equally, PQ over AB squared is equal to the area of triangle PQR over the area of triangle ABC. And so, if you know the lengths of two corresponding sides and the area of one of the triangles, then you can find the area of the other triangle. Using real numbers, suppose the length AB is 6 centimeters and PQ is 4 centimeters, and the area of triangle PQR is 42 square centimeters. We can find the area of triangle ABC. Linear scale factor is equal to AB over PQ, which is equal to 6 over 4, and that is equal to 3 over 2. Area scale factor is equal to the linear scale factor squared. 3 over 2 squared is equal to 9 over 4. And so 9 over 4 is equal to, now in our linear scale factor, we used AB over PQ. And so in the area, we also maintain the ratio. And so we have ABC over PQR. And so we have triangle ABC over triangle PQR. And so 9 over 4 is equal to the area of triangle ABC over 42 square centimeters, which is the area of triangle PQR. Cross multiplication. 4 times the area of triangle ABC is equal to 9 times 42. We divide both sides by 4, and the area of triangle ABC is equal to 94.5 square centimeters. Let's take an example. ABC and PQR are two similar triangles. Their areas are 225 square centimeters and 6 square centimeters respectively. If QR is equal to 28 centimeters, find BC. In the solution, if the triangles are similar, then AB over PQ is equal to BC over QR is equal to AC over PR. Then again, AB over PQ squared is equal to BC over QR squared and is equal to AC over PR squared and is equal to the area of triangle ABC over the area of triangle PQR. And so BC over 28 squared is equal to 225 over 196. BC squared times 196 is equal to 28 squared times 225. We divide both sides by 196 and BC squared is equal to 900. BC is 30 centimeters. In the same way, linear scale factor cubed is equal to the volume scale factor. If two solids A and B are similar, then linear scale factor cubed is equal to the volume of A over volume of B. For example, two similar cylinders have radii of 7 and 14 centimeters. If the volume of the smaller one is 640 cubic centimeters, calculate the capacity of the larger one. Radius capital over radius small cubed is equal to volume capital over volume small. 14 over 7 cubed is equal to large volume over 640. We divide 14 by 7 is 2, and so 2 cubed is equal to V over 640. V is equal to 640 times 8, and that gives us 5,120. We now convert volume to capacity in liters. 1000 cubic centimeters is equal to 1 liter, and therefore 5,120 will be equal to 5.12 liters.